Can AI help us connect trillions of smart devices? Welcome to the AI Show with John Koetsier. Right now, there are maybe 20 billion devices connected to the internet. It sounds like a lot, right? Laptops, phones, watches, like that, smart devices that we wear, smart devices in our homes, smart TVs, smart speakers, and of course, industrial IoT. I learned a little bit about this myself just in the smart home space about a month or two ago when we changed our Wi-Fi. And for about 30 days after that, I was changing devices everywhere that had to get updated. In a decade, however, those 20 billion devices could be 50 billion. And a lot of that is enterprise IoT. How will we manage that? How will we keep that secure? How will we keep everything connected? So Intel and the National Science Foundation have just funded research into this. It's machine learning for wireless networking systems. And to learn more, I'm going to invite three people who are directly involved in the project. We've got Vida, Ilderem, who's the VP at Intel for labs, and she's also director there. We've got Thyaga Nandagopal from the National Science Foundation, and we've got Wang from the University of Northern Carolina at Charlotte. I believe that's North Carolina at Charlotte. Welcome to the AI Show, everybody.
Hi, everyone. Nice to
have you. I think this is a bit of a record. This is the most people we've ever had at any one time on the AI Show, so it's a record. Welcome. Thyaga, let's start with you. We're talking about billions of devices here, and you're doing things around ultra-dense wireless systems. What does that mean? Can you clarify for that? What is an ultra-dense wireless system? How many devices are we talking about? What's the density?
Right. So just for context, your traditional 4G networks that your current mobile devices rely on typically can support a region that has about 300 to 2,000 devices per in the coverage area. But at any given time, maybe 20 to 40 devices are active at any given time. So that's the current density that we play with right now, which is why sometimes when you go to a stadium, your network doesn't work because suddenly everybody's using the device at the same time. And you know, even if it's only hundreds of people, you're having trouble. Yes. We are talking about future networks where we are thinking about device densities. Think of what a stadium, a crowded sports stadium. You are going to have tens of thousands in a small region. That's the kind of densities we are going to start from and go all the way up to millions of devices in a coverage area of a single cell site in a wireless network.
Millions of devices at one single cell site.
Yes.
Wow. Talk about, I mean, that obviously seems challenging just from a bandwidth perspective, but I'm sure there's other issues as well. What are some of the core challenges of networking in an environment like that?
So think of us, all of us, the four of us sitting here. So if any one of us have to talk to you, for example, John, I just raise my hand and you can look at me and say, okay, Thyaga, go ahead and talk first. Imagine if you were in a crowded room of 10,000 people. Everybody's raising the hand, me. Just you, John, trying to figure out who should I point to and who should I give an option to speak. You would be struggling to figure that out, right? And you have to be fair. You have to make sure that everybody gets a chance to speak. Just doing that can stress you so much. And that's the challenge, the biggest networking challenge that we have in the future generation of networks. Just for the base station to decide who should I give an opportunity to talk and make sure that everybody gets a chance to speak in a given amount of time so they can get their data across is one of the biggest networking challenges.
And that's just the first step. That's just the first. I mean, smart devices will often ping a network and say, yeah, I'm still here. Yeah, I'm still here. Right. And sometimes we see noisy devices that are doing that often, right? Like hourly or even more frequently. Right. And so we get upset about those a little bit. But Vida, what do we need to learn about networking in those environments?
So one of the challenges is you and I as humans, when we are on a call or something, we want to have continuous sessions. We don't want it to be dropped, or we don't want to see that sun going on our buffering, right? So when we talk about very dense areas, as Thyaga indicated, you have to serve not only people, but also objects. So one of the fifth generation 5G is doing is to bring in communication, addressing the things-to-things communication. So you're going to have very heterogeneous traffic in your network. You have human-to-human traffic, which could be video, is the most application which is being used today, workload. And then you have to have the capacity. Your network has to have capacity to address this need. And so managing the traffic for the different loads, a load from a thing, a device, is very different than a load from, for instance, right, what we're doing right now, streaming video. And the other thing is we need the throughput. We need high data rates, which means we get our information faster. Also, the stadium is a perfect example. When you have so many wireless devices there and with so many, air waves going around, you get lots of interference, right? So how do you manage that interference? So the heterogeneity of the network and the number of services we have to address is becoming very complex for our next generation wireless networks. That's what we are facing.
And there's different challenges. You talked a little bit about that. There's different challenges for different things, right? We're using a high bandwidth scenario right here where we need continuous contact, and there's video going both ways and audio. So we need that to stay good. What there's these things that ping in occasionally or a little bit here, or somebody loads a mobile web page, they need a burst of bandwidth and then it shuts off. I mean, this is a really, really complicated thing to solve, it sounds like.
Yes, indeed.
That's true. And that's why this collaboration with NSF is so important in this research area, because you have the discipline of communication, computation, and AI coming together to address these challenges, actually.
Let's talk about that a little bit, Thyaga. Let's talk about the projects that you awarded. Maybe give a little bit of context on the awards and what you're trying to accomplish, and then maybe give us a bit of a rundown on some of the key projects that you've awarded.
Right. So we traditionally have been funding a lot of work on networking. Much of the work that you see in 4G today have been realized through NSF research that has been funded in the past 10 years or more than that. So we have been continuing along the path, and we have been investigating a lot of 5G for a very long time. As part of that, one of we just heard about the complexity of the network and the challenges of managing the network, the decision-making process in real time, has essentially spurred us to think about, and the research community that is working on these problems, to think about, can we use artificial intelligence techniques, AI and machine learning techniques, to help take the human out of the loop and make intelligent decisions on the fly. So sometimes the decisions have to be made using data that we have never seen before, that a human just cannot learn in time to make the right decisions. So that's one of the challenges that the community has been wrestling with for a while. And we have been seeing a steady stream of projects that have been seeking to, maybe how come we can't use AI for these problems. So at the same time, we have Intel and NSF have been working together for many years now, almost 5 years now. Intel came to us and said, look, we see this as a pressing challenge that has immediate impact in the 5G sphere. Would you be interested in working with us? And we would love to do a joint program on this. Again, I just want to point out that Intel and NSF have run 5 or 6 programs right now before this particular effort. And we said, this is perfect. There's a continuation of this partnership. Let's continue. Let's do this. So we created this targeted effort that as a special call, which is on top of everything that we normally fund, but specifically addressing machine learning and its applications for optimizing network systems. And network systems could be wired and the wireless networks and the edge networks, where both of them kind of come together. And so this is the name of the program, Machine Learning for Wireless Network Systems. So ML wins, it's a pun, right? It's a well-designed pun, I would like to say. And one of the interesting things that we anticipated was we received an overwhelming amount of interest from the research community, which kind of, in some sense, was a very good surprise for us. We are glad to hear that there are so many people who are willing to challenge many of these problems. We got so many good projects, and I think our Intel partners and us are extremely thrilled to see the slate of awards that are coming out of this, which I think we can talk more. But they cut across multiple themes, right? So we are talking about using machine learning to optimize the design of the network, the core network, that is the wired part of it that you don't normally see. They're talking about managing the spectrum that is used by your radios to communicate with the base stations and other devices, and then the devices itself, right? The data that the devices send themselves. So if when multiple devices are sending data, and let's say these are sensors, how can you learn on the fly without having to send all the data back to a central server? Can you learn efficiently? This what you call as a distributed learning. So it cuts across multiple themes, and I think there are much more to explore. We wish we could continue doing more and put more money into this, and we will continue to do more in the future. But this was an extremely promising start for bringing AI and automated, autonomous management of networks into the network management and wireless network sphere.
Excellent. And we're going to get into one of those projects pretty soon. We're going to bring Wang into this conversation. I'll just ask you, one of the challenges that's probably topical and top of mind for you is, okay, we're in this dense environment. There's a lot of signals flying around. Now there's an emergency and the police need to communicate, or an ambulance, or whatever, fire services, that sort of thing. Are you thinking of ways of prioritizing traffic like that?
So network prioritization is one of the key topics in this thing, right? So how do you automatically prioritize and isolate traffic to provide service guarantees is an essential piece of any network optimization problem. And we believe that there are some projects that actually are trying to address that. Again, it's not always necessarily first responders, because that's an easier example to grasp, right? Yes. But more often than not, it's you want to send a tweet that needs to go out is probably more important. Or if you want to have a video conversation that you want to have that traffic prioritized more than somebody who's trying to watch a YouTube video, which is more of a one-way communication, which is not necessarily as critical. So these decisions, right? The first responder scenario amplifies it, makes it very crisp. But networks have to make these decisions on the fly all the time.
Yes.
And this prioritization is somewhere where artificial intelligence can excel, because it kind of can sense the traffic patterns and you can see traffic flow shifting. So for example, one can argue that if there's an emergency, yes, you have to prioritize the first responders, but you may also want to prioritize people who are tweeting about it, because that's information for the first responders to learn from. Interesting. Right? A human probably would not make the decision.
Yes.
However, AI can sense the fact that there's an event of interest, and therefore we need to prioritize traffic around the area of interest, and automatically make the cells, capacity from other cells, focus the energy from surrounding cells into that region. So the structure of the network itself changes dynamically really fast to prioritize more traffic in that area. So the tweets can get out, the videos can get out, and the first responders can also try and communicate with people on the ground. So that's something AI can do really well, and we are excited to enable that kind of solutions with this program, which we cannot do today with current network management solutions.
Interesting. And Wang, obviously we need that intelligence dispersed, right? We need that intelligence close to where things are happening, right? We need that intelligence in our Wi-Fi nodes and networks and our cell towers and other things like that. What's your project? It sort of looks like mesh networking.
Yes, somehow it's related to mesh networking. So overall, my project is to develop smart wireless multi-hop networks, such as mesh network, to enhance the AI performance of edge devices, such as cell phones, like robots, auto-driving cars. So that's the overall goal of my project.
Interesting. And talk about what we need AI to do there and what you're using it for.
So basically, there are two types of AI technology we are using for this project. One is called federated learning. Another one called reinforced learning. So the federated learning is basically it's an emerging distributed machine learning paradigm to improve data privacy compared with the traditional centralized machine learning. So when we talk about AI, basically we need lots of data to train the AI models. The data include personalized data. For example, like when you are using cell phones, like we have the smart keyboard from Android phone or iPhone, which can give you a next word prediction, or sometimes also can help you to finish the whole sentence, right? So actually behind that technology is the AI model. So however, in order to train the AI model, generally we need to collect the data from all the users and put the data in the central server. So that increase or raise a lot of privacy concern because people do not want to share the personal data. Definitely, you do not want the server to see what you are typing in the past, right? So how to solve this problem, which basically it's one of the key challenge faced by AI community. So now the federated learning is one of the solutions which can address the privacy issues. So the key concept is that we let many edge devices like your cell phones to train a global shared model by using their local without uploading them upload the data to the central server, so that we can keep the data local and private, but we still can get a very accurate and high performance global model. So that's how we can make the edge device smarter and smarter. However, we can keep the data private and secure. So
Nice.
now another technology we trying to do is using reinforced learning. So that's actually is regarding how we can develop smart mesh network, wireless mesh network to make the edge devices to be coordinated in a much more efficient and timely manner. So wireless mesh network basically is a low-cost communication infrastructure or paradigm, which use lots of wireless router that are connected to each other using wireless links instead of wire links, such as fiber optical cables. So wireless mesh network actually can provide much more low-cost and efficient networking services for large population people, including those people living in the low-cost community or low-income community or underdeveloped regions or rural areas. So the recent one of the example is like SpaceX Starlink satellite network, right? So SpaceX actually launched thousands of small satellites which can connect to each other to form a wireless mesh network, which can provide internet service to everyone on the Earth. So now we actually try to utilize the mesh network to coordinate the training process of the edge devices so that we can actually democratize AI by making AI accessible to everyone in the low-cost manner, including the people, like as I said, living in the low-cost or low-income regions. So then the reinforced learning actually can teach the network to make smart and optimized decisions so that we can improve or optimize the performance of the AI models by using the minimal training time.
Okay. Very, very cool. Good stuff. Vida, let's turn to you. We're getting more and more smart devices in our homes. Offices, factories are getting them as well. And currently, they may have local smarts, but they're reaching out to a network. They want to send some data to the cloud or other stuff like that. They just kind of reach out blindly, expect that there's a network that they can attach to. Are we going to make those smarter as well? How will AI change the picture there?
Very good question, John. So the way you look at it, the first instantiation for AI is basically efficiency, right? So if I have a device which is very power constrained, do I really need to keep pinging the tower when I'm not near a tower, right? So you can use that intelligence to, preserve your battery power, right? Your energy. That's at the device end. On the network end, the same thing. How can you boost the efficiency by the backend office to make it more productive, and you can have your return on investment on it. The other side, as Thyaga mentioned, is this whole workload balance because of type of services that are coming online. So we talk about very diverse and divergent requirement. You have a Twitter feed, or you have a video feed, or you have a parking meters waking up and sending a kilobits of data and going back to sleep, right? So how do you manage that so your network has the best performance to offer you the best quality of service and experience for the application you need? The third important part is the management of spectrum. Spectrum is a very scarce resource. It's a very expensive resource. You look at what FCC, does. You pay sometimes billions of dollars for this spectrum, right? So you have licensed spectrum, which is control. You have unlicensed spectrum like Wi-Fi. So your cellular base, your LTE, 5G are licensed. Your Wi-Fi, Bluetooth are unlicensed. And then you have shared spectrum. So what AI can help is if the spectrum is not used, maybe intelligently, it can access that spectrum for your managing the workload and the traffic in the pipe, if you may. So it brings the intelligence in there. And you have, every network has multiple spectrums to it, right? You have your LTE, 4G. Now with 5G, you have the new bands opening. So there are many, many spectrum waves going on. So the idea is also for AI to manage interference between these different spectrum accesses and usages. So there are many, many ways AI can step in and improve the next generation services, dynamically adjust the spectrum for optimal performance, and of course, improve the efficiency of devices and the network on both ends.
Interesting. And maybe spectrum hop to find a place where you can get communication and maybe say, hey, Wi-Fi is busy. I'll instantiate some Bluetooth mesh networking or something like that dynamically and go for it, right? Does that require AI specific chips? I mean, what are you doing there for on-device intelligence?
So depends. That's the question. So if you are on a battery operated devices, which are like set and forget in the field, and you want to process the data at the source, i.e. where you collect the data, so you need a very low power, efficient. So maybe you need a specific chip for AI to do that intelligence, at that node. But your node could be a remote, roadside unit, which you can use, more higher. This requires a higher performance. You can use your high performance CPUs or GPUs, general purpose GPUs, and in that case, you can say, hey, I don't need a very specific. What we have currently can be applied towards AI. So it depends. So there's a range of this. So if you're constrained for power, form factor, that type of thing, you probably move more towards ASIC or specialized solution. If you're looking at bigger workloads towards cloud and edge, then I think some of the existing solution may be sufficient. They have to be optimized for that workload.
Very, very interesting. Maybe I'll turn this question first to Thyaga, but others are welcome to jump in on this one. We've seen that smart home sometimes isn't so smart, and sometimes smart devices as well inside companies have been vectors for attack. I believe a couple of years ago there was an automated system in a fish tank that was a vector for attack in a company, and it was like a smart home device, smart office device, and that was just the way that the hackers got in. We've seen a lot of that in smart home with cameras and other things like that, bad security. What are the particular security challenges of very dense ecosystems? If we move to 50 billion, 100 billion devices globally, I mean, right now I might have, it might be 40 or 50 smart devices in my home. And in the future, it could be everything. Every window is smart. Every surface is smart. Every wall knows where it is. The roof and the gutters know when there's water coming down on other things like that. You essentially have a smart building envelope and interior. It's hard to count discrete elements of intelligence in there, but it could be hundreds easily. What are the challenges of security in that scenario?
So do you want me to scare your audience completely?
Absolutely.
So I think there are numerous problems. I think part of this has to do with scale. Part of this has to do with the fact that a lot of our devices are increasingly driven by software. And we all know software is inherently buggy, right? I mean, whether we like it or not, that's the reality of the situation. And also it comes from the fact that there are heterogeneous devices. It's no longer, we no longer use devices provided by a single vendor who controls everything. There are a multitude of devices manufactured and operated by many different people. And it's very hard to kind of know everything that's happening in the network. And of course, the last, is the last and most important one is a human factor, right? Ultimately, security comes from the fact that you can trust an individual to do the right thing, and when you no longer can trust the individual, there's nothing really you can do. So, this is like the macro, right? These are the macro issues. But if you look at the real challenges, number one, when you have millions of devices or even thousands of devices that are operating, traditional hacking and attacks have come from a single malicious device. Now, what is really worrisome to security experts is what they call as low persistent threats, right? So these are things where a small number of a large number of devices that are doing small things here and there that are not noticeable by a human being, right? Now, I send a packet here, you send a packet somewhere else at different times, and together you sneak out. You sneak and manage a big attack on the system. I mean, a simple analogy is a distributed denial of service, right? We started out with denial of service, which is a single device pumping a lot of traffic. We knew how to handle it. Now we have millions of devices pumping traffic, all directed to the single server. You cannot stop any one of them. It's much harder to solve, right? This is taking to the extreme. You could have, thousands of IoT devices launching different kinds of attacks. Now they could all be asking the base station, "Hey, I want to talk, I want to talk, I want to talk," drowning out anybody else who really has a real purpose to talk. A simple attack, right? They could all be saying that, "Oh, I am down. My network is bad in this area, right? I can't get your signal." And immediately the base station think that something is wrong with its with the signal propagation. So it's trying to adjust automatically, causes starvation somewhere else. So it's like a bunch of what I call as in the aggregate, when multiple of devices work in concert in a malicious manner, that can overwhelm anything that we know how to defend against today, right? This is what I call as like collective behavior. Now, of course, different vendors will have different IoT devices. Each of them may have their own software vulnerabilities, and any one software, creating a vector of attack, suddenly leads to you having to figure out where did this attack come from. The network operator has no idea, right? Why is this device, which was working fine until yesterday, is suddenly behaving? Is it behaving badly because it is misconfigured? Did the owner, the person who owns this device, accidentally misconfigure the settings to keep sending too much data? Or is it behaving maliciously? Mm-hmm. How do I, as an operator, decide? Or do I decide to shut this off and cause the customer to get upset? Or do I kind of figure out a way to call them up and say, "Hey, what's going on?" How do I alert them? So the operator has to make these decisions. And again, if you look at it, the scale becomes much harder. If it's 10 devices, 20 devices, it's easier to pinpoint and kind of isolate it. If you're talking about millions of devices, now this becomes a problem.
Yes,
right?
I can totally see that.
Exactly. And then suddenly you also have to worry about legacy devices. Some of these devices have to be supported for a long time in the network. Let's say I'm putting in an IoT sensor that is going to be embedded on my road or in the bridge. That is supposed to be transmitting the condition of the bridge for 20 years, right? Fast forward 10 years, and suddenly the sensor is either behaving as designed, or is behaving, or stopped working, or it's suddenly sending some random stuff. Now, how do I go figure this out, right? There's nobody who even understands what software is running on that sensor anymore, right?
Yes.
Now, so that's other problem. So a lot of it has to do with secure software development, number one. Of course, the standards themselves have to be secure, right? Because now increasingly we are moving into more of a software-driven ecosystem for the 5G and whatever comes after 5G. 4G and previous generations used to be much more hardware-driven. Now we are going software-driven. So the inherent challenges with the software bugs that we all face every day move into the network domain very fast. And of course, then there's a human element of it, because how do we as humans handle security challenges when we can't even communicate with the device? So traditionally, until now, our communication has been human-centric. We talk to other humans, or the humans are at least on one end of the communication, right? You're either consuming a video or you are sending something. But now what Vida pointed out is the machines are going to be sending traffic across each other. Who are you going to talk to figure this out? Right? So are you going to say, "Hey, machine, what are you doing?" There's no one to tell you. The machine doesn't know how to talk to you. So we need to have a language to figure out how to communicate and troubleshoot a machine. which we don't have yet. So these are some of the challenges we would have to solve, and to make these networks robust and secure. And again, AI plays a very important role in these things.
I can totally see that, and especially in security and understanding big patterns that are invisible to a human about what might be going on. Do we have a reliable estimate today of what percentage of network utilization is machine-to-machine traffic and what that might look like in 10, 20 years?
I'm going to defer to Vida because
I was going to say, I don't have that number. Sorry, you need a telco operator to tell you that.
That's okay.
I mean, anecdotal numbers. Yeah, anecdotal numbers have suggested that the number is rising, right? I remember a number from a couple of industry reports that talked about the number being around 10 to 15% in 2018, but it was growing at an annual rate. I mean, they're projecting that to be 50% or so by 2025.
Wow.
So that's a huge number, right? I mean, it's like growing pretty fast. Again, a lot of these are projections, of course, right? It all depends on how much we see IoT become prevalent and pervasive, and how much of it really relies on cellular network connectivity. A lot of these devices still use Wi-Fi, and for that part, we all know that your Roku devices and your home devices talk a lot in the background, even when you're not watching a video or
very talkative.
Right, they're very talkative, right? Now, we don't know what's going to happen on the cellular network. Will they continue to do so or not? But some of the projections are essentially showing rapid growth in that model.
Very, very interesting. Well, thank you all for participating in this. I much appreciate it.
Thank you so much.
Excellent. For everybody else, thank you for joining us on the AI show. Whatever platform you're on, please like, subscribe, share, comment. If you're on the podcast later on, hey, rate it, review it. Thank you. Until next time, this is John Koetsier with the AI show.